Okay, and I managed to save the last lectures because when I went to section 4, it got corrupted. Most of the stuff, my whole drive got corrupted when I connected. So the good thing is that since it's not MP4, it's .flb, so I was managed to be able to extract all the data. But it took me a long time, because every time I would connect the hard drive, it will crash Windows. Windows will crash. But I will manage to get those videos. So this time, I'm just gonna upload them as soon as I record them, and then delete them. Because it takes a lot of space. Okay, so we're just gonna continue on lecture 13. More while loop examples. We're gonna create the n factorial using a while loop. Last time we did it using a for loop. So this time it asks us to do, simply n factorial. Last time, remember what was the limit? Do you guys remember? What was the limit for an integer representation using integer data type for n factorial? No, I mean the actual number. Remember, if we do 13 factorial, can we represent it using an integer? No, right? So that means 12 was the spot on right there. Okay, so and that's because again we cannot represent a larger number, greater than 12 factorial using an int data type, because I think we have what, 4 bytes, I think. We can test it here. I remember Visual Studio was what, how you test it, you can say int size of int, right? And we did size of int, right? And then cout, we can say and this is size of an int in Visual Studio, right? And then here we have size of int, like that. End of the line. Save it. I'm going to debug. So we're debugging. So yeah, it's 4 bytes. So that means that we can only represent, 4 times. A byte is what? A byte is 8 bits, right? So 4 times 8, only 32 bits of resolution. So that will be 2 to the n minus 1, right? Maximum number that we can represent. So last time, I want to make a correction. Last time I think I was discussing 8, but I forgot. Visual Studio is 4 bytes. Okay, so just keep that in mind. So therefore, is the same idea as last time, but all we have to do is use a while loop this time. Okay, so a while loop. This is example for a product, right? So in this case, this is finding the n factorial, but it can be represented using the product. The sum of product, or no, the product expansion. So we can go here and then do our first test, right? We can say this will be variation 1, like this. So this is int n and then temp, right? And then we can say int answer is equal to 1, right? That is to hold the answer. Temp is simply to display the number. And then we can say cout, request the user to enter n in n factorial, right? And then we can ask also the user, obviously, we want to input the data, input stream. Okay, so then now we can let temp equals to n. That is to display at the end or answer. And then let's now do our while loop. Okay, n is greater than 1. Okay, then and again, this is because remember we're gonna factor out, or we're gonna decrement here because we're gonna start from what, larger to smallest. So the way I'm gonna do it this time is a little bit different. I'm gonna do answer, times equal, right? Because remember it's a product, right? So it has to multiply. For example, we put 7. It's gonna be 7 times 6 times 5 times 4 times 3 times 2 times 1. Right, so here we're gonna start at the answer to be 1, so it starts multiplying If we put 0 here, then we get everything multiplied times 0 will be 0, right? So you have to be careful on that. So the answer is 1. That is a good placeholder or a starting point. And then we multiply, we do what? We can do, ants times what? N, right? But in this case, we want to do, star equal for compound statement equals to n, right? And then we have to control, the loop control variable is n this time. So we do what? N minus minus, right? Because we want to do start at 7, for example, then go to 6, 5, 4, 3, 2, 1. Okay, and then next, what we want to do is, that's it. We want to just display the answer. So this is C out. This will be variation 1. Like that. Let me just copy this. Variation 1. Temp. Like this. Equal to. Right. This is just to the format. The factorial. This is answer. End of the line. And then another end of the line just to separate. Give me a new line. Separate the two variations. So here's a complete code. So again, n is our number, but again, we're going to decrement it by 1 every time we iterate until n is greater than 1. Okay, we cannot let n go to what? 2? 0, right? Because then again, if it goes to 0, then everything multiplied times 0 will be 0, right? You have to be careful on that. So that's it. Let's run without debugging. All right, so then we want to do n and n factorial. So we want to do, for example, 7 factorial. The answer is, so we have to put a space here or like this, like that. Okay, so let's close this one. Debug, start with debugging. And then 7 again is 540, and that it matches, or, oh, we didn't have it here. So maybe we do 5 and 6 to test it. So debug, start with debugging. We do 5. There you go, 120. And then now if you want to keep this running, remember what can you do? You can just put, a while true here and then make sure that it goes, all the output, right? And then if you want to quit it, you can just use cn. For example, if you want to keep this running forever, you can do while cn, right? Out in the outer loop, right? Maybe let's keep it right here. Yeah, it has to be outside because we have to reinitialize the variables. Not every time, but this one has to be initialized again. Okay, so then we can do this, and then after here, like that, Control KF. So every time, remember you put a, maybe Control Z as your exit point. Remember, for CN, then it will break this infinite while loop here. Okay, when you enter the key, right? Or you can just let this here and maybe enter -1 to continue to fail, right? But let's see if this works. Debug. Start with debugging. Right. So then here I'm gonna enter n in factorial. So I want to do 5, right? So then it's 120. I want to do 6, 720. I do 15. No, maybe I do 12. Right, that works. But if I do 13, that shouldn't work. Right. But now let me see if I do Control Z. Yeah, it quits. But then it doesn't give you the correct answer. You see that? So that's just if you want to keep testing your code over and over. But Control C is the exit point for also for CN while CN. When it reads that, then it will break out that infinite loop and then just go into return. That's just one way of testing it. You can also say maybe here, you can say while true, right? And then it will repeat this forever, right? But then you can say
maybe where's my CN? Right here, right? And then you can enter, for example, do a test, right? So you can say if, right, n is equal to -1, for example, as your sentinel control, you simply break out of that, right? Else, it will continue. So debug. So we're doing debugging. So here we can put 5, it works, 6, it works, 7, it works, but then I put -1, it breaks out of the while loop, right? So that's just one way to keep testing it. But again, it does help you have um, a nested while loop just to keep the code going. Okay, that's gonna be event controls. The next example. Okay, so let me just take, because if I don't take a picture right now, then I forget for the other section that when I talk, because I'm just making this as I go on the fly. So that's it. That's one of the examples to keep repeating over and over. Again, maybe you don't want to have this. Maybe you can initialize those outside the while loop, because every time you come back on the while loop, what happens? You redeclare this and reinitialize. So that might take some memory or some time, some very micro seconds or even nanoseconds just to declare it. But if you want to just put it, we can put it outside. But this is just one way to test it. Okay, so that will be variation 1. Variation 2, let me just delete this so we can just run all of them as once. So here I'm gonna delete that one and then delete this one. So that was variation 1. All right, so let's do variation 2. Using a while loop 2. So the next variation is like you can do maybe start at a start from, instead of going from the biggest number to the lowest, you go from the smallest number to the biggest. So you can do int, for example, or int I is equal to 2, and then do answer equals to 1, reset the answer, and then you want to say again, copy this, enter n and n, and then I don't think in this one you don't need a temp, because you're not going to be reducing n this time, so we don't need a temp here, and then simply call for n and do while I is less than or equal to n, right? Because again, we're going to start 1, maybe at 2, because again, that anything multiplied times 1 will be that number, right? So then again, if we can start at 2, we can start at assuming that we already did 1 times 2, right? So then in this case, we're going to say simply, say answer times equal to I, right? So we start from smallest to largest number, and then we do I plus plus, right? So in this case, we decrement, in this one, we increment. In this case, we need a temp because we're decrementing that number that we entered. In this case, we only use it as a comparison. And then we start, I at the smallest point. In this case, you can make it 1, but there's no need to. Because again that anything multiplied times 1 is that number itself. So again, we can copy this line right code right here, and then paste it. This will be variation 2, right? And then this will be n, right? And then answer, right? Again, the temp we needed because we were modifying the input number. So we want to go in debugging. So the first one we'll do 5, and then the second one we'll do 5 again just to test it. So it's the same answer. Okay. So those are the 2 variations. Again, we already did this in a for loop. So now I'll give you 2 variations on a while loop. Okay. So again, the maximum will be 12, because again, you cannot represent a very, very large number, beyond 12 factorial using an int data type. Okay. So with that said, let's move to the next example. Example 6. This is a while loop that we did in a for loop format, I believe. So in this case, let's just do it here just to get more practice. So let me save, let me choose delete this. You already have. So this will be lecture 13, is it? Yeah, 13, example 6, right? So we want to save that. And then we want to create a sum, int s for sum, set it to 0, right? And then we want to create int I, maybe start at 1, right here. See that? So we want to go all the way. What will be our limit here? 27, right? And then we can use that to modify as to go to 28, right? So then we can do that. We don't have to enter nothing because it's a fixed sum. So we can say while, I less than or equal to 27, right? Then we say that s plus, s plus equal to I, right? Then we do times, I plus 1, right? Because remember, we want to do 1 times 1, right? 1 times 2. So that's what we have. 1 times 1 plus 2. 1 is 2. So it's 1 times 2. And then here we want to do I plus equal to 2, right? So we want to make sure that it increments by 2. So the next iteration will do 2 times 4. The next iteration will do 5 times 6. The next iteration will be 7 times 8, all the way until it reaches 27, and then we'll do 27 times 28, and that where is our code ends, right? So here we do cout, example 6, and then s is equal to s, end of the line. So now here, we've been using the sum as being what? Being a integer, right? But I'll show you in a second. So let me just go ahead and do this. So that will be our answer, right? 3850. But like I said, we were used to using this as integer. Nothing stopping you from doing, for example, double, right? So for example, we do double of this, and then we can put 1.0 here, right? And then we do double sum as well. When you do double, can you also increment on this case? Can you use the plus equal for a double data type in this case? So let's see, right? The only thing is that we have to do what? Show point here, right? Obviously. So that's one key element here, right? That that if you're working with real numbers, right? You have to be careful that remember, if you're working with real numbers, that means that you have to use double, right, to store the sum. Now, what if I ask you to do fractions? Remember when you did um, the pi approximation, then you have to make sure that this is properly done here, properly divisible, right? The same thing here, right? If you compare, for example, this is a whole number, right? But what if, you want to make sure that, for example, maybe this becomes, it's a fraction, it's expression, right? So if you do say, as long as, I is greater than or equal to maybe 27, right? Or maybe say 1 divided by, say, 50, right? When you do this comparison, what does this tells you? What is this division? Someone? Huh? 1 divided by 50. 0, right? So you have to be very careful because then this will not behave. Say, for example, if I maybe do something like this, if I do a fraction, right? So when this happens, what is it going to do? Is it going to be testing for 1 divided by 50, or is it going to be testing for 0? In this case, it's going to be for 0. So what do you have to do to fix it? Make sure that this is a real number, right? So that therefore you can either do what? Put a do either point or one, or as long as one of them is a double, right? So see, now the expression is a double, right? So therefore you have to tell the compiler that you want that, because if you don't do that, then it's going to give you the incorrect comparison, or the correct testing for expression. So that means that the sum is going to be incorrect. Okay, so that make sure that in this case, we've been dealing with sums that compare only integers. And in the case that if you were to compare this number right here, make sure that you properly, initialize these variables. Because again, 1 divided by 50 with no, decimal point is going to be simply 0. Because again, the real part, gets truncated. So any decimal gets truncated and it goes to 0 in this case. Okay. So again, that is just, one way of expressing this. Let's see if this one works. I just made it up. So see, this one does not work, right? Because in this case, you're increasing what? I, right? And maybe it never finds, this is greater than, right? It will always, probably be here. So maybe can we move it like this? As long as that, debug, sorry. There you go. See, right here is 0, but again, because we started at 0, basically it skips it. So again, this was just for I was not meant to. If I fix it, I can just give you an example. But in this case, if you want to have this, like I said, maybe as long as this is greater than 1 divided by 50, make sure that and maybe you can do I plus plus here. Let's see if that one debug. Still stuck in the while loop. Okay. So again, this is just not meant to give you a sum, but it's meant to saying in this case we want choose to how is this fixed. Okay. So make sure that you use this properly in case it pops up in an exam or a quiz. Okay. That this has to be properly initialized. Okay. And it was not even part of the problem. I just want to make a clarification on that. Okay. So again, this is I need to fix it. I don't know. Again, I modify it on the fly. So it's not even the real problem statement. Okay. So with this said, let's move to the our next example. And then this is the one that I ask you to think about it over the, and I click a different part. Let me just. All right. So this is the next example I want is example 7. Okay. So this is an actual pretty interesting approximation because we use e to the x or a decaying exponential like e to the negative x, right, in ECE a lot, and you're gonna find that a lot in ECE because those are usually by Euler's identity. We can also represent cosines and sinusoids using the e expressions of e, right, using the Euler formula or Euler's identity. So that means that as programmers we can learn about this approximation. So as I explained last time, we said that e to the x can be approximated as 1 plus x over 1 factorial x squared plus x squared over 2 factorial all the way to plus n to the x to the n divided by n factorial. So each of the terms is going to be an approximation. So 1, 2, 3, 4, all the way to the n terms. For example, if we want to have a 5-term approximation, the 5 terms of approximation is going to have 1 plus all the way to x to the 4 over 4 factorial. Okay, so this means that since we want to make sure the code runs more efficient, we want to make sure that we don't use power, right? We don't use power, and we also don't use factorial from the CMAT library. So therefore, we can use a looping, where we can factor out the code as one or start from the center, right, which is 1 plus x to the 4 times 1 plus x to the 3 times 1 plus or maybe I'll rephrase it. I'll say 1 plus x to the 4 times x to the 3 plus 1. All that times x times x over times x over
to, plus 1, and all the resulting of that answer times what x over 1 plus 1, right? So that means that x can be a real number, right? X can be 1, 0, it can be 1.24, any real number. So that means that's what we want to approximate, right? Remember, E is a good, a real number that is used in math a lot. So that means that we want to approximate, say, for example, e to the 1.34. 1.34 takes the value of, x takes that value, and that's what we use it to approximate it here. Okay, so this means that let's see if we can develop the code for that. And again, this is my solution. You might find a different or a more efficient solution for this. Okay, so let's do that, and then I have it here. So again, please follow along, and then I'll go back and explain, how do we do this. So again, since x is going to be a real number, we start declaring it as a double x. Also, the sum is a real number, so double s, right, for that. And then now int, we can use for n the number of, number of terms, right? And then well, n is going to be not the number of terms, but it's going to be the number of terms minus 1, right? Remember, see this one right here? So you put 5 terms, what is it going to do? Is it going to do 1 and then x to the n uppercase minus 1, right? All the way to 4, right? So you see that? When you do 5 terms, this is not 5, right? So that's the reason why I use n, letter n and uppercase n. So because I'm going to ask, this is going to take the number of the number of, the exponent, say if you put 5, this is going to be 4 because it's going to be 5 minus 1, right? So then let's take it for little n as it's in on the solution, and then uppercase n for the number of terms. Okay, so I put a comment here, n is for the number of terms, right? So then I can say C out, enter x, right? N expo x, right? Exponent is like usually write like that in math in programming languages. You can see it here. For example, in MATLAB, I can approximate it here to see if we got the right answer. I can say expo of 1. See, that's my approximation right there. 2.783. And maybe I want to do format long answer. That is the actual number. Right? You can see that we want to write this code where we put expo and then we put the x inside. And again, this represents e to the x, okay, and it's a mathematical term. So then therefore we go here. So we want to enter x in x, the exponent, e to the x. And then we enter Cn, and then we go x. So you're going to enter a real number. And now you ask C out, because this is an approximation, so you say enter the number of terms, n, to approximate, right? And then you enter Cn, n, okay, like this. So now I want to call a little n equals to n minus 1, right? And then now I want to do a ternary condition. Again, you might do it not like this. This is choose a way of how to figure out things out, okay? I want to do the following. I want to say S, the sum, right? It's going to take, I'm going to test it, okay? I'm going to test if the number of terms is greater than 1, right? Then, I want to evaluate, and then if this true, then I want it to be 1 plus x divided by n, okay? And I'll explain this in a second. Else if this is true, this means that the number of terms is less than 1. So that means it's 0, right? So that means that in this case, no, maybe if it's 1, for example, right? Because 1 equals to 1, 1 greater than 1 is what? False, right? So then, if there's at least one term
right? I want to make sure that this is the approximation, right? So then more than one two terms. Look at what I'm doing, right? And then I'll explain this in a second. Okay. I'll do what 1 over x to the n. 1 plus x. And I'm now focusing not on this, but I'm focusing on this one right here. You see that? The first term. So you guys see this? You see that right there? I'm gonna work from the inside out. Okay, so that means this is my if if this fails, if this is true, then that means that we can proceed and do this term right there, 1 plus x over n. In this case, n is gonna be, for example, you enter 5, it's gonna be 4 right here, right? So we want to test this one first, okay, with 5 terms to make sure we got it right. So therefore, in this case, that's it. We handle that. You might do it differently, like I said. So what we want now is, now start with the while loop. While n greater than 1, right? Let's perform the following, okay? So now you see that. Now here's the trick. The next multiplication that we want to do is what? We want to multiply this two elements times what? X over 3, right? So then therefore, what we want to do here is that we want to do n minus minus. We want to decrement the n because we already handled the first one, right? We handle the first case. This is going to handle what? The second case, right? So then let's do s star equal, right? And then you do x divided by n. Okay, you see that? That will be here, this second term. And then how do we handle the 1? We do what at the end? S plus what? Plus equal 1, or what do you do to increment 1 plus plus? That's it, right? It looks very complicated, but that's it. We almost done with 80% of the code, right? All we have to do now is display the answer. So now let's do the following, right? If n is greater than 0, right? That means that we have successfully have correct terms, right? In case the user enters 0. So see out. Now you say fixed, show point, right? And then set precision maybe to 2, because we want to display the only x, right? We don't want to show 8 significant figures for x, right? Let's just make sure it's 2. And again, remember, we have to put it at the top. Include IO manip. Okay. And then now we say C out exponent of x. Close that. And then you say is equal to, like this. And then at the bottom now, change it to C out. Maybe I want to copy this one. Change it to 8 or 6, whatever you want. I'll do 6, right? And then here you do C out, the sum, and then this is using, now you say how many terms? You say n terms. You will end of the line. Saved. Okay, so now if if the user enters the correct amount of terms, right? That means that if you enter at least one term, you can approximate it by e to the x goes to 1, right? That's what the formula says right here, right? At least one term, even though it's incorrect, e to the x is what? 1, right? So that means that it does handles that. Now we put else, right? Simply see out, n must be greater than or equal to 1 factorial, right? No, not 1 factorial, sorry. Uh, one term, right? And then I can put exclamation. Sorry, I was confusing the exclamation with, and then end of the line, right? Like that. So that is it. So we're gonna run it and test, make sure that we tested the approximation first with the actual answer, and then we approximate how accurate it is with the actual, not the actual answer of the approximation using Wolfram Alpha, and then the approximation using the actual number in MATLAB, for example. Yes. Here you can choose to put whatever you want. I mean, it's just like just to tell you that the user enters 0 terms. Okay. So with that said, let me put it a little bit up. All right, let's compile. Build the solution. All right. And then let's test it first. Debug. Start with debugging. Let's test it for 0 terms, right? So let's enter 1.34 approximation for x, e to the 1.34, right? Hit enter, and then I'll put 0 terms, right? So that means, okay, that works. See, it tells you n must be greater than or equal to 1 term. So now let's debug it again. And then I want to enter the same number, right? And then I want to enter 1 to approximate. What will be the answer here? Huh? You sure? For 1 term is what? We're not even using x, right? For 1 term is 1, even though the approximation is incorrect. Okay, hold up. I don't know why it does that every time I move them. So it's 1.34, 1. Okay, so it says 1. Okay, it's still incorrect, but because we use 1 term, as we use more terms, it's gonna get more accurate. So let's do this, debug. Start with our debugging. So now let's do the actual. Let's do 5 on the example. So let's do 1.34. Let's do 5 terms. That is the approximation. Okay, so now let's check if this number is correct. Okay, how do we check that? Remember, we can go to Wolfram Alpha. Right, Wolfram Alpha. And then we can now type here, for example, you can type 1 plus x to the x divided by 1 times x, no, sorry, plus 1 x divided by 2 times 1 plus, x divided by 3, times, x, no, 1 plus x divided by 4. And it tells you, when as you close the parentheses, now you can say where x is equal to what? 1.34. Okay, 1.34. So let's see if this is approximation is correct. Okay, so let's put it in. So the answer is what? 3.77316. What do we get? Yeah, 77315 is the same thing. I have more precision, right? So the this goes to 6, right? The 5 gets rounded to 6 on Wolfram Alpha. So is the same answer or no? Yes? Huh? So that means that you didn't follow me through then. Okay, so now let's test it for one more, right? Let's test it for 5. Make sure we have this right. So then all we have to do is put 6 terms, sorry, 1 plus 1 x divided by 5, right? Like that. And then run it again, right? So it's 3.09 for the same answer. That means it's getting more accurate. So let me rerun the code. Debug. Start with debugging. So again, let's put 1.34. And sorry. 1.34. Enter. Put 6 terms. There you go. See? 3.99 is the same answer as Wolfram Alpha. Okay? So that's it. So we're confident that this approximation is correct. Yes? So now let's do more terms. Let's do 100. Let's see how accurate this goes. Okay, so debug. Start with our debugging. So 1.34, enter. How many you want? Maybe 100, right? Hit enter. So 100 is 3.819044 to 100 terms. Let's go to MATLAB and then put expo of 1.34. Okay, so where we have 3 point, very accurate, right? See that? 3.819044. That's what we got there, right there. See that? So the 100 terms is very, very accurate. So let's do more precision, maybe. Maybe change this to 8 to see how far we can take it. So close this window, debug, start without debugging. Now let's do the same one, and then 1.34. Enter, maybe let's do 1,000 terms. So we can see that how precise it is. So it's 81, 90, 43, 51. And then let's go to our MATLAB. Up to what precision? We got 81, 43, 51 right there. See that? Is after 1,000 terms is very, very extremely accurate. Okay. So this is what I'm talking about. Deriving this type of solutions. Obviously, I'm not going to ask you this on an exam. Because the solution looks, once you see it, it looks very straightforward, but then to get to that solution, that's the hard part, right? Like I said, sometimes when I was undergrad and they gave me this, I would stumble too. How do I find this solution? Even redoing it again for me, like it took time, like maybe a couple hour, 1 hour, to 30 minutes to an hour, just to make sure I got the correct, parameters. But again, this is what I was talking about mathematical approximation. This is more efficient. Why? Because it does not use how, it does not use n factorial, right? Because remember, if you use maybe if you do 12 terms for the larger, more than 12 factorial, what's going to happen? It's going to break, right? It's not going to give you an accurate result. In this case, it's more accurate because, the expansion becomes more and more accurate as you go because of the factorial, of the factor form, right, on the equation. So again, this is what I was talking about. Here's the code. Again, you might have a better version than me, because when I was discussing this in section 1, there was a student that actually did it right on the spot. Okay, and his version was different than mine. So again, this can be done. You know, I even said, you can do this over the weekend, but he did it in front of me. So, you know, again, you can go ahead and see how can you improve this, understand it, what is happening. Again, the reason is like we want to make sure that we work from the inside out. This is working inside out. This is the inside, and then this multiplies to the next row, and then we increment. This keeps repeating that process right here. See that? It handles this, the next term plus one, the next term plus one. This holds the product. Okay, S holds the whole product, because this whole thing gets multiplied times this, then plus that, and that whole result gets multiplied times that. So that's what this simple code is doing. The key here is this, that you start at n and then you store it and then you decrease and then keep doing that, over and over. Okay. And again, you might have a different solution. So if you do have that, then that's okay. Like again, because in coding is very hard to have one single solutions. Okay, an exact solution. This is my iteration. This is how I found it. It might be the best way or the most efficient, but it works. Okay. So again, that's food for thought. You can use that, study it, and then maybe learn more other approximations. Okay. So with that said, let's go to examples, lecture 14, and then choose. We'll do a few of them from there. I'm not going to do all of them. There's only 4. It says, right, you can do that. I'll probably do. We already did it, but we did it in a for loop. You can do it in a while loop. But I'll provide this code after tonight. Okay, I'll provide all the sample codes, all the C files. I'll put it in the folder so you can study it. But this one is too easy. I want to skip it. Make sure that because we already did it. You just want to convert that for loop that we did, do it into a while loop. Okay. Example 2. This is the one I want to discuss because it's actually pretty interesting, and then actually it's also part of math. It's also part of computer engineering, because if you're a computer engineer and if you want to go to network security,
network security, believe it or not, is purely math. You know, when I took a class in network security as a grad school, it was purely math. Like it was all we were working with, polynomials, and again for making the to have like a good encryption, for example, right? Because nowadays, if you don't have good encryption, then everything can be hacked. Okay, so right now our typical encryption is like for example RSA encryption, AES 256 encryption. The larger the bits on the encryption, the more harder to crack. The more hardware you need to crack it. But we're getting to a point where now everything's quantum. So now we're going into quantum encryption as well. So again, we're in that race. I think China is doing that. Is encrypting most of the data to a satellite they have already on orbiting Earth. Most of the encryption they're trying to do, their testing is through quantum encryption. So, the Euclid's definition for the greatest common divisor is used as very important calculation, and it's used in coding. We use it a lot. We use it in computer security, again, for RSA encryption. And again, you'll learn more when you get into that, into your if you decide to take a network security class, you will learn more about this. You will learn about prime numbers too. How to find the largest prime. The larger the prime number, you can use those primes for encryption too. So again, there's not only one branch, but again, it branches out to multiple ways on how we use this. So, for example, the Euclid's definition of GCD, it says that if you have a GCD of A B, right, it will be A if B equals to 0. Okay. Else, this is not true, right? If B is not 0, then what we do is we basically swap. We say GCD. We will swap A with B, and then now we have comma A mod B, right? And this is assuming obviously that making the naive assumption that A is greater than B and B is greater than or equal to 0. Okay. So we can have an example. So, for example, we want to find the greatest common divisor between 85 and 81 and 45, right? Then you can say that GCD in this case, we see that B is not equal to 0. So what do? We flip A, we swap A with B, so we now becomes 45, comma 36. But what is 36 found out? 81 mod what? 45, right? That is the remainder of that, ordinary division. So then we repeat the process until B becomes 0. So then you can see that. Then we do GCD, swap it again. Now it will be 36 with 9, right? And then again, in this case, you have what? 45 mod 36 is 9. And again, you keep repeating, you swap it again, and you do 9 um, mod 0. But then again, it will be 36 mod 9 is what? In that case, is 0. So in that case, B becomes 0. So therefore, what is the greatest common divisor? It's 9. Okay. So you can see that why? Because 81, is divisible by 9. 45 is also divisible by 9. So then this is how you find that. Again, we can probably turn this into a function. For now, we can use it as a formula. What do you tend to turn into a function? You can do a function call and create GCD, and then input two integers A and B, and then it will spit out the greatest common divisor. For now, we always just can use as a for loop. So this will be our example. So let's go and then delete this one. And then let's do our example. So the example will be as follows. So how do we find this? We say int a, b, and then a temp, b temp. This is just to store the variables temp and for a temporary measurement. Okay, like this. Oh, I forgot to put a comma there. Right, and then you say cout, right, and then enter a and b in GCD A, comma B, separated by space. Okay, then you do CN A, CN B,
All right, and then you do a temp. Simply store it there. Say a, and then you do b temp. And again, this is just for printing it at the end. Okay, and then you do while b is not equal to 0, because remember that's where we break. Right, that will be our ending point. As soon as b equals to 0, then we need to end the while loop. Okay, so while it's not equal to 0, that means it's going to be true as long as it's not equal to 0. Then we say temp equals to a, right? We swap the variables, right? So we move temp equals to a, and then now a takes the value of b, right? This is the swapping of the variables right there, okay? And then b, what is it? What does b become now? Remember, b is a mod. Yeah. So then this case, we want to do temp because that's where we store a, right? Because remember, we did the swap already. So then it's temp mod b, okay? So like this. So this means that, if we go back to our definition, we can see that as long as b is not equal to 0, right? That's when we store it, and that means that this remains the same right here, right? If b equals to 0, then we skip this whole while loop and go and print out your answer. But in the case that b is not equal to 0, then here, see, this is where the swap occurred right there. But before we do that, we need to store temp a into temp so we can use it later. So we can see that going back to this analysis, then B becomes what? A mod B, right? So that's why we do it here. Here is where A is supposed to be, is that temp mod B, so therefore we have this swap, and this keeps going until what? This operation becomes what? 0, right? Because what happens when this becomes 0? Right? It becomes false, right? Because 0 not equal to 0 is false, right? Because it's actually true, right? So then, therefore, that's it. That is our answer. So then we can say GC out, GCD, and then now here's where we use our temporary variables. We say a temp, and then comma b temp equals to a oh a temp, right? So we want to get the final value of a, right? So then we put end of the line. That's it. We save it, and this is a whole kernel. And then later, this kernel can be put into a function, which we're going to learn next time, and then you can reuse it anytime you want. But for now, let's test it. So we want to have start without debugging. So we want to enter maybe 85. The test that we have 85n. No, sorry, 81n 45, right? So the greatest common divisor will be 9, right? So we hit enter to see that. But now here, what happened? Why do I have 81? Oh, because it's btemp, right? Yeah, debug. Start debugging. Okay, let's test it again. 81 space 45. It is 9. Okay, we can do another test. Debug. Start with debugging. Maybe we can say 24 and 8, right? The greatest common divisor will be 8. Okay. Debug. Start with debugging. Maybe do say 81 and 12. It's 3. Okay. So you see it works. Again, we always use this for loops, while loops. Okay. Very easy kernels to understand. Okay. We're gonna probably come back and use that at create a function, and then maybe use it later on for some computation that we can do. Okay. So that is it for that one. For that example, again, all the source code are going to be put out tonight, so you can study them in case you didn't understand quite what was going on today. But again, it feels like everyone's following what's happening. Again, you can do this one. We already did the factorial. All we have to do is put in the event control, which is quit as when you put -1. We showed you one earlier, but I'm pretty sure I'm confident that, when I put the code, you understand it. What I do want to do is this one right here. Okay, this is example number 4. We already did one of the patterns, but we want to make sure now that when you put 0, it quits, but then it grows as you put larger numbers for n. Okay, so in this case, we already have the code that we used before, right? We already did this one already, the 5 printing pattern, but now we want to make sure that it's more dynamic. So it quits when you put a 0. So let's do the following, right? So let me erase this whole thing right here, and then I want to do int n, right? And then I want to do cout, input n, okay? And then I'll say cn n, right? And then this is where you say while, n is not equal to 0, because that's when we want to quit. So you want to make sure that, we have a entry point. So that's where we're going to enter, right? And then now we use the same code that we used last time. For example, remember it was located in the, I think it was lecture, this one right here. It was in nested loops. We use this code right here, right? So let's use this one right here. Copy this code right there. Go over here, paste it here, and then what do we have to modify? Because this is for large to big, so I have to do is change this to goes to 5. Let me see right here, right? It goes to 5, right? But in this case, it will go to what? 2. We can put anything we want, right? So let's put n, and then it has to be greater than or equal to 1, right? And then I minus minus, right? Like that. So I think that's the only modification we have to do. Yeah, like that, okay? But in this case, n is, we can put any larger number that we want, not only 5, okay? So in this case, that's it. I don't think, I don't know, I like the way it looks there, but it's okay. Now, how do we handle this quitting again? Can we put a cn at the end again? Can we copy this 2 lines, right? So once it's done printing, what is it going to do? Is it asks again, right? And if the user enters 0, what happens? It breaks out of the while loop. So this is what we call event control. The event is decided by you, the user, okay? So that means that's it. And then if the code ends, you can simply say cout, bye, right? You're leaving, right? End of the line, right? Like that. All right, and then so let's build this project. So again, if I put 0, what happens? I quit, I don't go into the while loop, and then it says bye, right? But then let's rerun it again. And then now let's say, want to enter what? I want to enter 5, the example that we have. So you can see that it starts to grow. Maybe let's put 6. It gets bigger. 7, bigger. 8, see that? 9, 10. And then can we do more? Maybe let's do 15. No, I want to do 50 maybe. 20, 50, right? See that? And then now if I put 0 here, what happens? It's gonna happen, set by, okay? So that's what we call an event controlled. It's very similar to a sentinel because you know what value to put in. But again, event control can be either happen by macro operations when you do mods, for example, or when the user enters a number to quit. Okay, so for our next class activity, we're going to have something very similar like this. It's going to be next week probably. And again, it's because now we're just getting ready for our midterm and finalizing all these lectures. So then we can now, be move at the more much faster pace now because now we went over a lot of examples today. Okay, so again, I'm gonna post this online today. But before we move on, I just want to close all the statements, all the this lectures with a final lecture that is not long, it's pretty short, is basically the conditional operator. Remember we said we're going to talk back about it. What happens here? How do I do full screen? I don't know why it's, let's see, close this. But the thing is that it's not letting me. Oh, now it works. Yeah, for some reason it was locked. Okay, so this is the conditional operator, and then it just has several examples that we want to go over. But you can see that last time we said that the conditional operator, it was also called the ternary operator because it depended on three elements. Okay, it depended on expression one. And if expression one is true, then we move expression two is the winner, right? Else, if expression one is false, expression three is the winner, right? So inside, you can either have a value that is assigned into a variable, or expression can execute an actual expression inside of it. Okay, so we can see that this type of a statement is called the conditional expression. Okay, so if expression one evaluates to a non-zero integer. It doesn't have to be always one, right? It has to be at least true. Remember, non-zero is true. So this is that is also to true, right? The result of the conditional expression is expression one. Otherwise, is expression three. So to just give you one example is the absolute value, right? For example, find the actual value using a single line. So, the following program will obtain the absolute value of a number. So this is using your typical if else statements, right? So this will enter x and y, right? And then, no, you enter only x and then you'll get y depending on x, right? So you say enter any integer. It can be positive, it can be negative. So what do you do then? Then it says if x is less than zero, this means it's what? Negative, right? If it's negative, simply negate that negative to make it a positive. Else, y becomes simply x, right? If it's positive, the absolute value of a positive is simply positive. So you can see that. So here we simply display absolute value of x is simply y. So this, see how many lines we have to use? You have to use one, two, three, four, and then the printing. So you have a lot of this. It uses four lines here. These four lines can be replaced into a single line. So you can see that. What is the conditional operator equivalent of the previous code? We can write the same thing. This is the same as before. Int x, y, and then enter any integer. And this is the new updated line right here. See that? So you can say that. You can say y is equal to, if x is less than 0, that means it's negative. Then what happens? This becomes true. So then we execute which one? This one, right? So then expression becomes what? Negative x, right? We evaluate the expression, so that becomes positive, and then it gets assigned to y. We ignore this one in case this fails, okay? And in case this is true, then we ignore this one. Else, if x is greater than 0, what happens? We ignore this one, and then we go into x. So then x gets stored into y. So as simple as that is, simply the what we call the conditional operator for absolute value example. Okay. So in this case, it's very straightforward. As long as you know that it uses three terms. Now, can you have maybe nested ternary operators? Yes. You see that I think you saw my solution, right? Many of you who are studying my solutions for maybe go fall semester 1310. I think it was one of the homework. No, class activity. You saw that? I think it was class activity number 2 solution. You'll see that when I go here, I have this solution that requires look at how many if else statements. But then if you go into solution number 2, look at that one single line of code to handle that. You see that? That uses a ternary operator within a ternary operator, right? So again, it's much as long as you understand it, it's much simpler because it's one single line. Okay, so I'll explain that, probably later or study that on your own. But I'll explain one that is very similar. For example, finding the maximum of three numbers, right? So if you want to find the maximum of three numbers, that is A, B, and C, assuming that all the variables are properly declared, you're going to see that you can use two if else statements. No, you can use a single if else statement, and then you can use nested if else as well. So you'll have, see this one, if A is greater than B, A is the winner. But now we have to test what? A against C, right? So then, and if, let's say this is true, right? Then we go into what? A greater than C, right? Then A is the biggest of the three, right? Else, well, what happens? C is the biggest, right? Then the same thing. If A is less than B, what happens? B is the winner, and then we still have to test B against what? C, right? If B is greater than C, then B is the biggest, then else, C is the biggest, right? So you can see that C is the one that we test at the end in this case. But again, look at how many lines of code we're using. This can be replaced with one single line of code. Okay, that's the advantage. So that means that using, we want to write, see, now write a code fragment that does that, answer, max of A, B, and C. This is like saying a function. We're not in functions yet, but this will be the mathematical representation of that. So we can see that by the exclusive uses only of the ternary operator, the conditional. So how is this done? We use the same thing. We want to test A first, and then if that is true, we move into test it A against C, right? And then else we test B against C, and then the result will be that. So will be the winner either will be C or B or A or C. Okay, so let's do it right here. So this is the answer, right? The solution, you can see that here's our first test. Okay, so if A, is greater than B, then I put parentheses to separate the operators. So this is the second expression. This expression is what? This is expression one, expression two, and expression three on my ternary operator. But you can see that inside expression two, I have what? Another ternary operator. So therefore, you can see that A greater than B, then we test what? A against C. So then if this is true, right? So let's test this one first. If this is true, what happens? We go here, right? So then now this means that A is greater than B. Let's test A against C. So A is greater than C. If that is true, what happens? A is the winner. So A goes where? Into answer. What happens if A is less than C, which is this is false? Then C is the winner, and then C goes into answer. So we use parentheses to make group the ternary operators. In this case, you don't need it, but it's easier to read. So see here, if A, basically is bigger, then A is the winner. So you jump in here, but then you still have to test it against C. If A is less than B, then we avoid this whole expression, and what do? We simply say B is a winner, but then we still have to test B against C. So then now if B is greater than A, then what happens here? We have to test it against C. So if B is greater than C, then B is the winner, the absolute winner, and then B we store it in A. But if this fails, what happens? C is the winner. So you can see that, this can be as complex as you want. You can have as many as you want internally. With this, you should be able to understand the solution that I had for the class activity number two. But again, this one, again, the elegance is one line versus, look at how many, if you can count it, this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, lines versus one line, right? So that's the advantage of using that. So you will see it. You will see me using that a lot more and more as we go for the function part. Okay, so that is that modular increment. We can discuss that later, next class before we go into functions. Modular increment, modular decrement. What I do want to discuss is something that I left off, with that I want to use a closing statement for, for selection. This is what we call ambiguous or if or dangling if. Okay, This is a problem on almost any programming language that is, is basically handled by the compiler, but it's what we call this ambiguous if or dangling if. So, for example, assume that all the variables are probably declared and consider the following statements. You have if a greater than b, right? Then you go. If that is true, you go inside and test. If a is greater than c, you see out hello, and then else you see out goodbye. So the problem in this if statement is, or maybe the question that you ask yourself, when is the last output will be executed? In this case, for example, what happened if a is less than b? What will you print? See, that's the problem, right? Because that's actually the dangling if. You don't know how the if else is grouped because you have what? You have two ifs, there's only one else, right? So now here's the solution, right? This is called the ambiguous if or dangling if. The ambiguity is resolved, okay, by it resolved by understanding how the compiler works. In this case, the ambiguity is resolved by associating the else, right, which is the only else that we have in that segment, with the closest s less if. In this case, what is the closest s less if? This one or that one? The closest will be this one. So therefore, it might think that this is associated with that, right? But not. The compiler, what it's going to do, the compiler is going to associate this with this one, right? So that's what we call the dangling F. This one is actually, if you treat this as a one, this one, it will be a one-way selection only because you test it first and then it goes into a two-way selection internally, okay? So this, ambiguity is resolved by, associating the else with the closest else plus f. But what happens? You don't do it. The compiler does it for you. What are the consequences of such resolution? That means that if A is greater than B and A is greater than C, right? The code prints hello, right? However, if A is greater than B, but A is less than or equal to C, the code prints goodbye. Now, finally, as soon as you read that A is less than B, the code's not going to print anything, right? Because of the dangling or ambiguous if. Okay? So then again, this is done for you by the compiler. Indentation does not determine the pairing, but it communicates the pairing. Okay? Obviously, the compiler does it for you. If you start typing in Visual Studio, that indentation is done already by Visual Studio. Okay, but if it didn't do it by Visual Studio, then you might think, okay, the outer if is paired with the else at the end, but it's not. Okay, we want to do the closest s-less if. Okay, so that is choose a closing statement because usually it's not discussed that well in that book in Malek, but I just want to just talk about it. Finally, you already know about this, but it says careful when you see equal equal, and then this is equality and this is assignment. Okay, assuming that all the variables are properly declared, the following statements, what are they going to do? B is equal to 0, A is equal to 3. If A equals to 5, then say B equals to 7, else is B equals to 9. What will the code print? It will print 7, but why 7 when A equals to 3? Can someone tell me? I think we discussed this before, but not in detail. And then 5 is a non-zero, right? And then becomes true. So ideally, this is what we call a logical error because you're what you actually want to do is do what? Change this to equal equal, right? In case you want to test for equality. So this will be the replacement. See that? So now if you fix it and put equal equal to 5, now what is it going to print? It's going to print 9 because this, 3 is equal to 5 is false. Then it goes into, it's going to print B. We skip this statement, and then B is equal to 9. Okay. So that is that. That is the only warning. Most likely you can use it here, the equal sign. But when we test for condition, we always use equal equal. Okay. Make sure you don't make that mistake. So that's it. What are the words? What are some of the final words for the midterm? Um, the midterm is prepared. So whatever we did in I type here or whatever's in the lectures, it's gonna nothing's gonna be new. There's gonna be no surprises. Okay, so the only thing that I want to say is that maybe if whatever we talk is you should be able to do it on the midterm. The only thing that I want to mention is that maybe just before we everyone goes is that for 1310 I think is one of the take home quizzes, take home quiz 2. This is section 4, right? So solution. When I meant about a flow chart, remember the best way to do is say you always see a flow chart, right? On my lecture notes, it will say flow of the while, flow of the if. I wanted to see this. These are the actual symbols of the flow, right? Oval means start and end. The square means process. So that's where you can just tell the clear variables. The what is this? What is this name shape? Is like a not a trapezoid, right? No, it's a rhombus, right? So with the rhombus means either input or output, okay? And then you can see that that's why this the end. This is the diamond means decision, okay? So you can see that it's very clear to follow. This is copied from the notes exactly as this. If this is true, call that number, sum and count. Keep doing that until this is false, and then print the sum, and then at the end, do another final decision. If you have counter not equal to zero, so get used to this. That's what I meant. Study this one. The symbols are online. I make this in PowerPoint actually. I didn't use Visio. I just made it in PowerPoint and then pasted here. Because in PowerPoint you have the same symbols and they snap, right? And then it's very easy to create that. Again, um, that is that. I'll end it here. But the let me stop